Hello and welcome to this new video. We are now in chapter 3, and in this video I'm going to cover section 3.1 about Laurent series. Okay, so Laurent series are a generalization of power series, and they include negative powers as well as positive powers. So by definition, a Laurent series is a series of this form, a series of powers of n, but we include negative powers as well as positive powers of z minus a. This is a Laurent series about z equal a. So we say that this series is convergent if the two series of positive terms, or non-negative and negative, both are convergent. Okay? If both parts are convergent, we say that this Laurent series is convergent. Okay, and there is this similar definition for absolutely convergent, uniformly convergent. Now, the series of non-negative terms is called the regular part. So this is the regular part of the Laurent series. And the series of negative powers of z minus a is called the singular part. You understand why? Because there's a singularity at z equal a. Okay? So every Laurent series is composed of the sum of two parts, the regular part and the singular part. Okay, so let us establish our first result. The domain, so we know that for power series possess a disk of convergence, possibly infinite. So there is a radius of convergence. For Laurent series, the analog of disk is an annulus, possibly infinite. Okay, so instead of one radius of convergence, we have, if you like, two radii of convergence. So a Laurent series usually converges in an annulus, okay, which could be actually a punctured disk. If I take P2 equals 0 here, it's possible that P1 equal plus infinity and P2 equals 0. It's possible that this annulus is empty, right? Because if P2 is bigger than P1, it's empty. And I will give you an example shortly. So a Laurent series actually possess what we call an annulus of convergence, which is possibly empty, or the whole complex plane without A. Okay. So why this? Where do the number or the values P1 and P2 come from? They come from the decomposition of the Laurent series into two parts. So if you consider the regular part, it has a radius of convergence, which is possibly, it could be 0, it could be infinity actually. These are the extreme cases. So we know that in this case, this power series converges inside the disk and diverges outside the disk. First thing. Now, if you consider the singular part, and we write it as a power series, but so I do a change of variables. If I put 1 over z, u equal 1 over z minus a, I can write this singular part as a power series about u, about 0, with another variable. So this power series, again, has a radius of convergence, okay, that I call R2. Okay, so by definition, or by the properties of power series, this series is absolutely convergent inside the disk of center 0 and radius R2, and divergent outside. Therefore, if I let P2 be the inverse of this radius, then the singular part is absolutely convergent if I replace u by 1 over z minus a, this is equivalent to saying 1 over z minus a in modulus is less than R2, or if you like, if you inverse you will get z minus a in modulus bigger than 1 over R2, which is P2. So we have absolute convergence outside the disk of center A and radius P2. Okay, and that's it. If I combine the two results, so when do I have absolute convergence? I have absolute convergence if z minus a is less than P2 in modulus, and z minus a is bigger than P2 in modulus. So when we combine both, we get the annulus of convergence. Okay, now if you just a remark, so this concludes the proof of the first result. If you consider this power series now, and when you let u tends to 0, we get 0 actually, because the first term, so because we start with p equal 1, so we start with b1. So when you put u equals 0, we get 0. And now when u tends to 0, if I go back to the change of variables, u tends to 0 if and only if 1 over z minus a tends to 0, which means that z minus a tends to infinity. So it means that the limit of the singular part as z minus a tends to infinity is 0. Second remark, the annulus of conversions may be empty. If you consider the series of all powers of z, negative and positive, this, if you decompose it into two parts, you will see that actually here the radius of convergence of the regular part is 1 because it's a geometric series. And for the same reason, if you take the singular part, you'll get that P2 in this case is also 1. So here P1 equal 1 and P2 equal 1 as well, because it's 1 over 1. So this series, this Laurent series, is nowhere convergent. Or if you like, it's convergence on the empty annulus. Okay? Because modulus, the set of Z whose modulus is between 1 and 1 is empty. Okay? So we may have this extreme case. Next result, it's about uniqueness. So you probably know that if two power series are equal, then they have the same coefficients. You probably proved, we didn't prove that in this course, but you probably proved it in another course in the second year. And now we have something similar for Laurent series. If two Laurent series coincide on an annulus, on a non-empty annulus, of course, then they have the same coefficients. So this theorem actually, you don't need to know about the uniqueness of power series, because this is the uniqueness of coefficients of power series is a particular case of this result. Just take an equals 0 for n less than, for n negative, and bn equals 0 for n negative. So this contains the uniqueness of coefficients for power series as well, because power series now are a particular case of Laurent series. Why this is so? Okay, call S of z the common value of the two series, okay, which converges in the non-empty annulus. And so just draw a picture. So consider an annulus of center A, and so you draw two circles inside, one inside the other. Any z in the annulus can be written as A plus REI theta. Okay? Where R is what? Is the modulus of Z minus A, and theta is the argument. Okay? Since Z minus A is between P2 and P1, so R, the distance between Z and A, is between P2 and P1. So when I replace Z by its value, right? So Z minus A equal R EI theta. So the series becomes sigma of AN times R EI theta to the power N. Okay, because this term here is Z minus A to the N. And we know that the series is normally convergent with respect to theta. Okay, this is a property of, because it's normally convergent on a circle inside the annulus. Okay. Therefore, if you multiply by E minus IP theta and integrate term by term, what happens? So the integral of the sum becomes the sum of the integrals with respect to theta. The A and Rn do not depend on theta, so I can put them outside. Now, if you look at the integral, this is a familiar trigonometric integral. If P equal N, or N equal P, if you like, this becomes 2 pi, because I'm integrating 1, e to the I0. And if P is different from N, then this is 0, as you may check. Because we have an antiderivative of EI n minus p theta. So it's EI n minus p over theta over n minus p. And since by periodicity, we get 0 because the exponential is 2 pi I periodic. So actually, the only term surviving, actually, when I do the summation over n, the only surviving term is 2 pi AP to the RP. The remaining ones are 0. Okay? So when I integrate against E minus IP theta, I get 2 pi AP RP. Right? And if I do the same thing with sigma of Bn Rn EIn theta, because it's the same sum actually, we get the same result. So when I integrate, we get 2p BP Rp. Therefore, these two guys are equal, right? And therefore, AP equal BP. But since P was arbitrary, we get the result. Next result, if F is holomorphic outside the disk and vanishes at infinity, or tends to 0 at infinity, then I can expand F in a Laurent series with only a singular part. Okay, this is a lemma, if you like, a preliminary result to prove the next result, actually, about expansion of a holomorphic function on an annulus in a Laurent series. Okay, but this is a particular case of the next result. So once again, if F is holomorphic outside the disk and vanishes at infinity, then we can expand F in a Laurent series with only negative powers. Why this is so? By a change of variables. So if we set u equal 1 over z minus a as before, and we let g of u to be f of z, so this is the change of variables, then what do we get? Since f is holomorphic outside the disk, it follows that g is holomorphic on the punctured disk of radius 1 over r, right? Just because composition of two holomorphic functions, okay? So if f is holomorphic, g is holomorphic, but the domain is different because by this change of variables, the outside of the disk becomes the punctured disk, okay? And the point at infinity corresponds to 0, actually. Okay, by this change of variables. Okay, so when z minus a tends to, or z tends to infinity, same thing, u tends to 0. Okay? And now I use my assumption that f vanishes at infinity. Of course, when modulus of z tends to infinity, the modulus of z minus a tends to infinity. It's the same thing, actually. So it means that g has a limit as u tends to 0. Okay, so I can extend g by continuity by setting g of 0 equals 0. And in this case, what do we have? We have a continuous function on a disk, which is holomorphic on the punctured disk without its center. And we already proved in chapter 2, as a consequence of Morera's theorem, that this implies that actually G is holomorphic on the disk. Okay? So if you like, once again, we shall see now, so we'll say that 0 is a removable singularity of G. Okay, and therefore, by the theory of chapter 2, we can expand G in a convergent power series. Of course, we start from 1 because G of 0 equals 0, so B0 equals 0 if you like. Okay, and convergence happens in this disk. Okay, this is the main result, the first main result of chapter 2. Okay, that a holomorphic function is analytic. Okay, and that's it. So when I replace u by its value, I go back to f, I get this expansion of f. And this ends the proof. Now, the next result is about existence. We've already proved uniqueness of Laurent series. Now we prove existence of Laurent series for functions that are holomorphic on a non-empty annulus. So this is the result. It states that a holomorphic function on an annulus of center A has a Laurent series expansion about A. Okay. So if you like, it's the analog of the main theorem, I think 2.6 or something there. So the main theorem of the first big theorem of chapter 2 was that a holomorphic function is analytic. A holomorphic function on a disk is analytic. But now we are trying to prove something more general. A holomorphic function on an annulus has a Laurent series expansion. Okay, so it may include negative powers as well as positive powers. And this is a consequence actually of Cauchy's integral formula that we formulated in the last chapter. Okay, so consider a point Z in the annulus. You draw the annulus. I think a picture is will make things more clear here. So what do we have here? We have an annulus, so we have the center at A. We have the inner boundary, which is P1, and the outer, which is P2, sorry, and the outer boundary is P1. And we take two circles of radius R1 and R2 inside the annulus. So I have actually 4 circles now. First circle of radius P2, okay, this is the inner boundary. A circle of radius R2, a circle of radius R1 bigger, and the outer boundary, which is P1. So please draw a picture. And now call the circle of radius R2 gamma 2 and the circle, the outer circle, by gamma 1. So I have 4 circles here, and the inner circles are actually called gamma 1 and gamma 2, and they are positively oriented. So I think if you draw a picture, things will become more clear. Now, it's easy to check that gamma 1 and gamma 2 are A homotopic, because the straight-lined homotopy happens in A once again. So it's just if you like, a homotopy of center A, okay, shrinks gamma 2 to gamma 1, right? So this is an application of, now, not all homotopies are good like this, but this is the case here in this case. Okay, so so this is the straight-line homotopy which happens in A. So gamma 1 and gamma 2 are A homotopic. Therefore, I can apply Cauchy's integral formula, which I stated in this way. So 1 over 2 pi I times the integral over gamma 1 of f of u over u minus z minus the same over gamma 2 equal to f of z times the difference of the indices. Okay, now where is z? Okay, z is inside gamma 1 and outside gamma 2, if you draw a picture. Therefore, this is 1 and this is 0. Okay, and therefore this is just f of z. So f of z is actually the difference of these two integrals. I call now the first integral as f1 of z, it's a function of z, and the second one I call it f2. Okay, and we are almost done. Now we proved in chapter 2 a theorem on the differentiation under the integral. This was, I think, theorem 2.5. It follows from that theorem that this function of z is actually holomorphic, okay, because it's the integral of a function of two variables. It's continuous in both variables and holomorphic with respect to z. Okay, because everything is well defined. U is never equal to z because u is on the circle and z is inside, and here z is outside. Same thing. So f1 and f2 are holomorphic, right? So yeah, they are holomorphic out. Okay, on the complementary of the. So in particular, f1 is holomorphic on the disk of center A and radius r1. And so therefore, by the theorem of chapter 2, f1 has a power series expansion about z equal a. Okay, and convergence happens inside that disk. Similarly, for now, f2 is actually holomorphic outside the disk, actually, and converges to 0 at infinity by standard estimate. When z tends to infinity, this tends to 0 actually. Okay, it's not difficult to prove. Therefore, by the previous result, I can expand F2 in a Laurent series with negative powers outside the disk. So if I combine these two results, I get a Laurent series expansion of F. Okay, the regular part comes from F1, and the singular part comes from F2. Right? And that's it. Now, if you look at the coefficients actually related to these integrals that depend on R, actually, on R1 and R2. But actually, they do not depend. Why? Because of uniqueness of the coefficients. So actually, the coefficients do not depend on R1 and R2. I can take any R1 and R2 satisfying these two things. Okay, so I can take any R1 between Z minus A and P2 and any R2 between P2. So they do not depend on the radii of the circles. Okay, now let us give some examples, practical examples. Let us find the Laurent series expansion of 1 over Z minus A in the annulus of center 0, whose inner boundary is the circle of radius 1 and the outer boundary is infinity. So this is, according to our definition, is still called an annulus. So if you like, this is the outside of the circle of the disk of center 0 and radius 1. So the outside of the disk is called an annulus as well. So the first thing to do, so if modulus of z is bigger than 1, then 1 over z in modulus is less than 1. So the idea is to now factor by z and make appear 1 minus 1 over z in the denominator. And now we see that this is a geometric series of ratio less than 1 in modulus. So I can expand this fraction here as a power series as 1 over z to the n from 0. But I have the 1 over z outside. So when I put 1 over z inside, I get 1 over z n plus 1. So if you want to compute it, you can write it as 1 over z. We start with n equals 0, so 1 over z plus 1 over z2 plus etc. So all the negative powers of z. And there's no regular part here. So the Laurent series consists only so there's only a singular part here, and so negative powers of z. Next example, Laurent series of e to the 1 over z in the punctured plane. So this is just, if you like, another notation for C star. Okay, so C star is also an annulus according to our definition. Okay, so we just write the Taylor expansion of e to the z and replace z by 1 over z. And so we get 1 plus 1 over z plus there is a 1 over n factorial here, excuse me. So I missed the 1 over n factorial. So this is 2z2 and then 6z3 and so on. Okay, so 1 over n. So 1 over n factorial is missing here. So we see here, so what is the singular part here, and where is the regular part? The regular part is just a constant, and all this series actually is singular. Next result, let us find the Laurent series of this function, 1 over z2 minus 3z plus 2, in the annulus. This is a normal annulus, if you like. It's between the circles of center 0 and radius 1 and 2. Okay, so the idea is, I think that most of you will think of decomposing into simple fractions, and this is what we should do. Now, there is a trick here. Now, of course, there's a systematic way of decomposing. You write a over z minus 2 plus b over z minus a, or vice versa, and then you find a and b by identification. But there is a trick here. If you write 1 as z minus 2 minus z minus 1, you get a quicker decomposition. Okay, so this is what I should, and then actually Okay, now if z in modulus is less than 2, then z over 2 is less than 1. And if modulus of z is bigger than 1, then 1 over z in modulus is less than 1. So what I do is, in the first fraction, I factor by 2. Okay, and I change the order. Okay, you know why? Because I want to expand this in a geometric series. And in the second fraction, I factor by z. And now we are almost done. I expand, so this is something of the form 1 over 1 minus q, q less than 1 in modulus, so I expand it in a geometric series. Okay, and I do the same thing for the second one, but the ratio here is 1 over z. And so I can write it in this way, if you like. So the second series actually gives me the singular part. Actually, yeah, because I can start with from 1 here. If I put the 1 over z inside, so it becomes 1 over z n plus 1. Okay, if I do the change of variables, so I replace n plus 1 by n, I get this. So this series here is equal to this series, and this is the singular part. And the first one will give me the regular part. And that's it. Okay, now, of course, if you are tired, you can pause the video and continue later. Now I'm going to talk about isolated singular points of a function and classify them into 3 classes. Okay, so what do I mean by, first of all, a singular point of a function f is a point where f is not holomorphic. Okay, now if in a neighborhood of this point it's the only singularity, we say that it's isolated. So A is an isolated singular point of a function f if f is holomorphic on the punctured disk of center A. So I remove the center. This is a fancy notation for BAR without A. Same thing. Okay, so it's an annulus, it's a punctured disk, it's a disk without its center, same thing. Okay, so we know from what preceded that I can expand f in a convergent Laurent series in this annulus. Okay, singular part, regular part. And now let us look at the singular part. Okay, now the singular part could be 0. Nothing prevents that the singular part to be 0. So f consists only of a regular part. We saw an example earlier. Okay, so if you let A denote the set of integers such that A minus n is not 0. Okay, so this is a set of the integers. Okay, so it's the set of indices of the coefficients of the singular part. So 3 cases may happen. Either A is empty, okay, so there's no regular singular part, there's only a regular part. Second possibility, A is not empty, but it's finite. So this series stops at a certain index. And third possibility, A is infinite. Okay, so infinitely many coefficients are not 0. Okay, in the first case, we say that A is a removable singularity of f. In the second case, we say that A is a pole. And the biggest integer actually is called the order of the pole. We'll get back to this. And in the third case, we say that A is an essential, so small a is an essential singularity of f. Okay, and now I'll give examples. Okay, so if A is empty, so we just have a regular part. So even if f is not defined at A, I can extend it by continuity by setting f of A equals small a0. So f extends to a holomorphic function. And so examples of this. For example, the function sin z over z. Apparently, there is a problem at 0 because we are dividing by 0. But this is not really a singularity, actually. It's a removable singularity. Why? Because if I expand sine in its Taylor series, okay, I start with z minus z cubed over 6 plus etc. When I divide by z, I get a regular part, so 1 minus z2 of 6 plus etc. So I can extend f at 0 by setting f of 0 equal 1. And then I get actually a continuous function on C which is holomorphic on C star, and I know that actually it's holomorphic on C. So f can be extended to a holomorphic function. So 0 is not a real singularity, it's a removable singularity. In French, we call it singularité artificielle. Okay. Next case, capital A is not empty, and the maximum of A is P. Okay, so A minus P is different from 0. So we can write f in this way. So the singular part is finite, and the leading coefficient, so the coefficient corresponding to the biggest power is not 0. In this case, we say that A is a pole of order P. Okay. So we have two information here. The coefficient of A minus 1 plays a very important role, and we shall call it the residue. It's very important because it's the only surviving term when we integrate. Because when you integrate a Laurent series term by term, okay, all terms have antiderivative except this one. So this is why we call it the residue. So A minus 1 plays a very important role. We shall get back to this in the next section. And the P actually is the biggest integer, or the maximum of A, if you like, is the biggest element in capital A. And if A is a pole, then the coefficient should be non-zero. Okay. So for example, if you consider the function z sine over z4, and we do as we did before, we get what? We get a singular part consisting of 1 over z cubed minus 1 over 6z plus the regular part. Okay, now what do we see here? What is P here? P is 3. The residue is minus 1 over 6. Okay, so z equals 0 is a pole of order 3. Now, in the third case, we say that A is an essential singularity of F. For example, if you consider e to the 1 over z, that we expanded actually before, it's 1 plus 1 over z plus 1 over 2z squared plus etc. The singular part is infinite. Okay, so z equals 0 is an essential singularity of F. Okay, now I'm going to give 3 characterizations of isolated singularities. So first result will give 3 equivalent conditions to a removable singularity. Okay, so if we have a holomorphic function on the punctured disk, or the annulus z minus a between 0 and r, same thing, just a different notation for the same thing. So it's equivalent to say that A is a removable singularity of F. We know what does it mean. It's equivalent to saying that F has a limit as z tends to A. It's equivalent to saying that modulus of F has a limit as z tends to A. And it's equivalent to saying that modulus of F is bounded on the annulus, actually, or some smaller annulus. Okay? I should put another R here, small r if you like. So an annulus inside the annulus. Okay, because even if F, I should put small r here, a small r less than capital R, because F may tend to infinity at the boundary. Okay, but I just need boundedness around A. Okay, so it's a local property. Okay, so I'll try to prove to do a circular proof. So 1 implies 2 is almost obvious, because by definition F extends to a holomorphic function on the whole disk, and therefore it's continuous, so it has a limit. Okay, 2 implies 3 is trivial. 3 implies 4, less trivial. If modulus of F has a limit, then modulus of F extends to a continuous function that I call G. Okay, on a neighborhood delta. So delta should be less than R. Okay, so call this delta, and delta less than R. So it's a disk inside the punctured disk, or a disk inside the disk. So this function is continuous on the compact set B prime A delta. So this is an error here. And therefore it's bounded. Okay, so 3 implies 4. 4 implies 1. Okay, I expand first f in a Laurent series because I know that from theorem 3.1 that I can do that in the punctured disk or in this annulus. And now if I take a circle of radius small r in the disk and do something similar to what we did in the proof of proposition 3.2 about uniqueness, then I have a formula for the coefficients. Okay? So when I take the modulus, I get that the modulus of 2 pi APRP is less than the modulus of the integral. But the modulus of the integral is less than the integral of the modulus. And therefore, when I divide by 2 pi, okay, I get this estimate. Because now this supremum as a constant does not depend on theta. Now, my assumption tells me that f is bounded locally near A. So I can call it M. I can call this supremum M, or it's less or equal than small m. Okay? And therefore, this estimate, so APRP is less than, so I can rewrite it as modulus of AP less than a constant times r to the minus p. So I multiply by r to the minus p. Now, that's it. If p is negative, then minus p is positive. And so r to the minus p tends to 0 as r tends to 0. And therefore, AP is 0 because AP does not depend on r, actually. So therefore what? Therefore, all the coefficients with negative index are 0. Therefore, there's no singular part. And therefore, there's only a regular part. And this means that A is a removable singularity. Okay, so this concludes the first characterization of removable singularities. Now we are going to talk about poles. Okay, we give two characterizations of poles of order P. Okay, so same assumption. F is holomorphic on a punctured disk or an annulus. So it's equivalent. There is an equivalence between three conditions. A is a pole of order P. I can write F as the quotient of a holomorphic function over a power over z minus p to the A. And the limit of modulus of f of z as then z tends to A is infinity, plus infinity. Okay, so let us prove first one implies two. Okay, so we proceed as we did before. So we first write f in a so we expand f in a Laurent series. Okay, so this is the regular the singular part. This is the regular part plus sigma. Okay, this is a sigma here. Okay, no, it's correct. So the singular part is a minus p over z minus p up to a minus 1 over z minus a. So all this actually is the regular part. And since it's a pole of, since A is a pole of order P, the coefficient, the leading coefficient should be not 0. Okay, so if I reduce to the same denominator, I get this expression. Now, the numerator is actually what? Is actually a power series, right? And so I call it G of Z. And G of Z is A minus P, right? Because G of A is minus P because all powers vanish except the first one. And this is not 0. And this is just 2. Two implies 1 is easy actually, because if G is holomorphic, I can expand it in a power series about A. So because it's analytic near Z near A, okay, and then I divide by Z minus A to the P, and I get what actually? I get a Laurent series expansion of F. And if you look at the leading power here, P, the coefficient is B0, but B0 is G of A. B0 is G of A, which is not 0. So it means that A is a pole of order P. Now 2 implies 3 is easy because if f can be written as g over z minus a to the p, take the modulus. The numerator tends to g of a, which is not 0, and the denominator tends to infinity, or to 0, so the inverse tends to infinity, because it's a positive number times infinity. So f tends to infinity in modulus when z tends to a. 3 implies 2. Okay, so in particular, if modulus of f tends to infinity, then it's bigger than 1 outside, so in a punctured disk, okay? And then I do a change of variables, h of z equal 1 over f of z, okay? Now, then since f does not vanish here, then the inverse is holomorphic. So the inverse of f is holomorphic, and it's less than 1 on this punctured disk of radius delta. And according to the previous proposition, modulus of h is bounded. Therefore, A is a removable singularity, and we can extend H to a holomorphic function on the whole disk. Okay, so the center is included now, and I may still denote the extension by the same symbol. Okay, to simplify the notation. And moreover, actually, if when this extension satisfied h of a equals 0, because f tends to infinity, so 1 over f tends to 0, so h of a is 0. Okay, so what do I have? So H is holomorphic around A, and H of A is 0. Okay, now it's possible that H prime of A equals 0. So I let P actually be the smallest integer such that, so the first coefficient is not 0. So BP is, if you like, here is the first non-vanishing. So P is at least 1. We did something similar in chapter 1, actually. So P could be 1. Okay, if H prime of A is not 0, P equal 1. If H prime of A is 0 and H double prime of A is different from 0, then P equal 2, and so on. So I can factor by Z minus A to the P. Okay, and times a holomorphic function. Okay, we did something similar. And now I do just go back to F. So F is 1 over H. And I call 1 over G small g. Okay, it's holomorphic because capital G does not vanish, right? At least on a neighborhood of A. So on a neighborhood of A, I can write H as a holomorphic function over Z minus A to the P, and that's it. Okay, so everything happens here locally about A. And now the last result is a characterization of essential singularities. So there is an equivalence between saying, so same assumption about F, holomorphic on a punctured disk or an annulus. So it's equivalent to saying that A is an essential singularity. The image of any punctured neighborhood of A is dense under F, is dense in C. This is known as the Cassorati-Weierstrass theorem. And third condition, modulus of F has no limit as Z tends to be. Okay, so very interesting result. Okay, now before I do the proof, let me establish 3 conditions equivalent to condition 2. What does it mean to say that the image of this punctured disk is dense? It means that any complex number is the limit of a sequence in f of b in f of this neighborhood. Okay, and that's it. So any w in C is the limit of f of Zn, where Zn is a sequence in this punctured neighborhood. So same thing. So this is the definition. It's one of the characterization of density. Okay, and it's possible to take Zn. So it's possible to why, because if Zn is in this punctured disk actually, then Zn has a conversion subsequence. So I may replace the sequence by the subsequence. Okay. And second condition is also a characterization of density. A set is dense in C is if every non-empty open subset of C meets the set, which is f of B of this punctured disk. So just the same thing. Okay, or any disk of center W and radius delta meets this. So just 3 reformulation of the idea of density, okay, that we learned in the topology course. Okay, now let us prove 1 implies 2. Okay, why is that? So we reason by contradiction. It's not so. So I use the characterization 2 or 1, if you like. Yeah. Yeah. Or let me use the characterization 3. What is the negation of this condition? For every epsilon between 0 and r, and for every w in C, and for every delta, the disk BW delta meets the image of this punctured disk. So the negation would be there exists epsilon, there exists W, there exists delta, such that the disk does not meet F. Okay, so what does it mean that this disk does not meet the image of this punctured disk? It means that any element here cannot be in the disk, so it's outside the disk. So its distance to the center is at least delta. So if Z is in BA epsilon, the punctured disk BA epsilon, then its image is at least, its distance to omega is at least small delta. Therefore, so if I take the inverse now, the inverse would be holomorphic, at least on this locally, okay? Because it's the inverse of a non-vanishing holomorphic function. So G is holomorphic, and it's bounded because the denominator is bigger than delta, so the inverse is less than delta, right? So what do I have? I know actually either from proposition 3.4 or so yeah. So if it's from proposition 3.4, what do I have? I have a holomorphic function on a punctured disk, which is bounded, and therefore it extends to a holomorphic function on the whole disk. So in particular, it has the limit. Okay, and this limit cannot be equal to 0 because if g of z tends to 0, then the denominator would go to infinity. Okay, and if f of z minus w tends to infinity, then in particular f of z in modulus tends to infinity. And by the previous proposition, a would be a pole, right? But a is assumed to be an essential singularity. Okay, so if I extend now g by continuity to the whole disk BA epsilon, we have that G is holomorphic on the whole disk, the unpunctured disk, with G of A is different from 0 because G of A is L and L is different from 0. And therefore, if I take the inverse, would be holomorphic on the same disk. And we have what? And now the limit of the inverse to capital G is G of A is 1 over L. Okay, but the limit of capital G, so capital G is actually just f of z minus w because it's the inverse. Okay, and so what do I have here? So if f of z minus w converges to 1 over L, then f of z tends to w plus 1 over L. Okay, and by proposition 3.4 about removable singularities, I conclude that A is a removable singularity, and this is once again a contradiction. Okay, so what was wrong actually? My assumption was wrong. So the negation is true, and this is just 1 implies 2. 2 implies 3 is easy. So I use the density. So take W equal 1. Then by density, there is a sequence Zn converging to A whose image tends to W, which is 1. So in particular, modulus of F tends to 1. If I take W equal 2, I get another sequence converging to A, whose image under F converges to W, which is 2 in this case. So modulus converge to 2. So I have two sequences whose images, so I have two sequences converging to A, and their images converges to 1 and 2. So this means that modulus of F has no limit. And this is just 3. Now 3 implies 2 is just a consequence of the previous two proposition, because if modulus of F has no limit, then A cannot be a removable singularity, because if A was a removable singularity, F should have a finite limit, and could not be a pole because it doesn't tend to infinity. Okay, and that's it. So this concludes the proof of the last result, and concludes this video about section 3.1. Next time I will cover the residue theorem, and we'll finish actually the course, and then we'll solve some exercises, and then we will either meet online, or if the university opens, we will meet at the university. Okay, I prefer if you meet at the university because it's really a headache to. Okay, the connection is not always good, actually, as you may know. So please check when it opens, and okay, we'll agree on a date to meet live. Okay, so thank you for your attention, and goodbye.